In the previous video we fitted our posterior distribution using the OTFI method. And now that we have approximated our posterior distribution using well-known existing distributions, we're going to draw a trace from this posterior distribution. So in order to do that, we're going to define trace. That's going to be equal to approx. That's what we called the approximation above. We're going to sample from it. And let's say that we want to have 5,000 draws from this from our approximation of the posterior distribution. Then we say the number of samples is equal to 100. So that's the samples that we're going to draw from the posterior predictive distribution. We're going to specify the range across which we want to have these samples. So we're going to specify that this is NP linspace from 0 to 6 times pi from the NumPy library. And this is the number of samples that we're going to draw. Then we say with the model that we have, which we call time series kernel. I have GPC is equal to GP conditional. I repeat the name of the variable GPC. And that's XP, so that's that range that we just specified, same range that we specified above. So then we get PPC equals to pymc3 sample posterior predictive. We're going to sample from the trace, which we just defined. Fars is going to be equal to GPC, so our x variables, and then the number of samples that we want here is equal to n samples. Let's see whether we make any mistake here. No, it seems to be running, so that seems to be working fine. And now we can plot. So PLT plot. So we're going to plot on the horizontal axis XP, and then on the vertical axis we're going to plot our posterior predictive values. So we transform it to get it into the right shape, otherwise matplotlib might complain. The color is going to be gray, and we can specify an alpha. So this transparency of 0.2. So this is going to be our predictions, and we're going to add to our figure the data that we generated ourselves, and we're going to plot that in red. So let's see whether we made any mistakes here. No, apparently not. So the dots are our observations. So see, these are the same as the blue dots that we had before in the previous picture. And our prediction across this interval, so this is the in-sample prediction, because we're predicting across the interval where we already have observations. So the in-sample predictions are these gray lines. Yeah, so the important thing to note here is that our predictions are not points as they were before, but this is a Gaussian process, and as I explained before, a Gaussian process means that we're drawing from a multivariate normal distribution, so we're drawing strings of values, and each line is such a string of value. Yeah, so the picture is a bit small, so apologies for that, but you can see these sort of gray lines, certainly when you plot it yourself in your notebook. You can see these gray lines apparently at the edges most clearly. So each such a draw is a string of values, is actually a line. It's not just a point that we're drawing from our posterior distribution. And when you look at it like this, actually the fit seems to be quite good. So we're following this upward trend, and we pick up quite a bit of the periodic nature of our data as well. But of course, plotting inline is plotting in sample. I'm sorry, not inline. Plotting in sample is of course one thing. So let's see what happens when we try to plot out of sample. So we're going to do, the code is very similar to what we had before. So we again specify a number of samples. Here it's 100. Now I'm going to define a new variable xtest. And xtest starts at 6 times pi. So basically our test values start where the time series itself ends. And then it goes on from 6 times pi to 6.5 times pi. And also in this out of sample prediction, because now we're going to predict somewhere over here, so from where we actually do not have observations. Again, this out of sample predictions, I want to have 100 samples as well. Yeah, so n samples here are 100. This code is very similar to the code that we saw before. So with time series kernel, now I specify GPC test. Yeah, so not to use the same variable that we had before. So then we get our sample posterior predictive, also on test, on our test interval. And we're going to sample again 100 of them. Now we're going to plot. So this is the same plot that we did before. This is our in-sample prediction. This is the scatter of our real observations. So this is the line that is new now. And here we plot xtest. So this is beyond the time horizon where we actually have data, and our prediction here. So let's see whether we make mistakes here. No, that seems to be going well. So the first part of this graph is actually exactly the same one as we had above. But here now you see these green draws. And again, these are lines. These are not points, these predictions. And the green ones, as we specify over here, this is our out of sample prediction. Yeah, so these are our posterior predictions over the interval xtest. And as we specified, xtest begins where the previous interval ended. Yeah, so we get here our predictions after our observations on the time series have stopped. And although the fit here is actually quite good of our Gaussian process, you can see that, presumably what you were expecting was again something moving upwards. But this Gaussian process does not predict that, and the reason is this periodic effect that we have here is actually not baked into the Gaussian process. Yeah, so although it captures these points quite well, it actually does not pick up the fact that we have some periodic effect here, and therefore we would be expecting a move upwards here. It simply looks at the correlation between points, and its prediction is to go downwards, which may or may not be correct, so that's a different thing. But if you think that for your time series this periodic nature is actually important, what you can do is to look at the Gaussian process. So look at the GP, which actually has a periodic kernel. Yeah, so that's what we're going to do next. Look at the Gaussian process, which explicitly takes this periodic effect into account. So the kernel that you choose for your Gaussian process is actually important. Yeah, if you believe that this periodic nature is part of your data, you should choose a Gaussian kernel that reflects that belief.